All right, let's jump right in. Today we're going to be talking about diffusion models and how they can create these like super realistic images from just a text prompt.
Yeah, it's pretty incredible stuff.
For this deep dive, we've got a couple of really good blog posts. One's from Assembly AI and the other is from Medium.
Both of them are focused on image generation with these diffusion models.
It seems like everywhere you look now, people are talking about diffusion models, especially for image generation.
Yeah, they're really taking off. It makes sense, though. I mean, the quality of the images you can get is just mind-blowing. It's like DLE2, right?
Exactly. But before we get all caught up in the hype, let's try to break down how these things actually work.
Right. We need to get to the core technicality.
So first things first, what exactly are diffusion models?
Well, at a basic level, they're a type of generative model, which means they can be trained on a set of data and then, create new data that's similar to what they were trained on.
Okay, so in this case, the data is images, and the model is learning to create new images that kind of look like the ones it's seen before.
Yeah, exactly. But here's the thing. Unlike some other generative models, diffusion models, they don't try to directly copy the training data. They do something kind of different.
Interesting. So how do they learn then?
Well, there are basically two steps to the whole process. The first step is called the forward process, where you basically take an image and you gradually add noise to it.
Add noise, like making the image all blurry and distorted.
Yeah, exactly. You keep adding more and more noise until the image is basically just like pure random noise, like static on an old TV.
So it seems counterintuitive, right? You're trying to teach the model to create images,
Hmm.
but you're starting by destroying the images it's learning from.
It might seem that way, but there's a method to the madness.
Hmm.
By adding this noise, the model actually learns how the image degrades over time. It's kind of like watching something slowly dissolve.
I see. So the model is learning like the underlying structure of the image, even as it's becoming more and more obscured by the noise.
Exactly. And this leads us to the second step, the reverse process.
Okay, what happens in the reverse process?
So in this step, the model is trained to basically reverse the noise addition. So it starts with that super noisy image, and it tries to figure out how to remove the noise step by step until it gets back to the original image.
Ah, so it's like taking that static-filled image on the old TV and slowly cleaning it up until you can see the picture again.
Exactly. And the key here is that the model isn't just memorizing how to denoise specific images. It's learning to predict the noise component at each step, which is a much more general and powerful approach.
I'm starting to see how this two-step dance of adding and removing noise is really at the heart of how these diffusion models work.
It is. And it's this unique approach that allows diffusion models to generate such high quality images. They're not just copying, they're understanding the underlying patterns in the data.
So it's more about learning the essence of what makes an image rather than just, pixel by pixel replication.
That's a great way to put it.
Okay, so this noise that we're adding, it's not just random noise, right?
No, exactly. No, it follows a specific type of distribution called a Gaussian distribution. And there's also something called a variance schedule that controls how much noise is added at each step.
A variance schedule, what's that?
Well, it's basically a way of controlling how quickly the image degrades. It's kind of like a recipe for how to add the noise.
Interesting. So you're not just dumping a whole bunch of noise on the image all at once. It's a very controlled process.
Exactly. It's about adding the right amount of noise at the right time. And this variance schedule, it plays a crucial role in making sure the reverse process works properly.
Okay, so we've got this noise addition, this variance schedule, but what about the networks themselves? What kind of neural networks are used in diffusion models?
So there are a few different architectures that can be used, but one of the most common ones is called a UNet.
UNet. I thought those were mainly used for image segmentation, like identifying objects in an image.
Yeah, that's true. But it turns out that the UNet architecture, with its symmetrical design and skip connections, it's actually really good for image generation as well.
Okay, so we've got this two-step process, the variance schedule, and this UNet architecture. Starting to feel like we're building up a pretty complex system here.
Yeah, there are a lot of moving parts, but it all comes together to create a really powerful and flexible model. And there's another important piece we haven't even talked about yet, the training objective.
The training objective, what's that?
So basically, it's what the model is trying to learn during the training process. In the case of diffusion models, the objective is to maximize the likelihood of the training data, which basically means that the model is trying to learn the probability distribution of the data.
Hmm. So it's like the model is trying to learn the rules of the visual world so it can create new images that follow those same rules.
That's a good way to think about it. And to do this, diffusion models, they use a mathematical tool called KL divergence.
Scale divergence. That sounds pretty technical.
It is. But basically, it's a way to measure the difference between two probability distributions. So in this case, we're comparing the distribution of the generated images to the distribution of the real training data.
So scale divergence is like a measuring stick, telling us how close the generated images are to the real ones.
Yeah, exactly. And during training, the model tries to minimize that difference.
Okay, I think I'm starting to get the mathematical side of things, but I'm still a bit confused about how we go from this world of continuous probability distributions to the actual pixels in an image.
Ah, that's where the decoder comes in.
The decoder.
Yeah, so throughout the reverse process, we're working with these continuous probabilities, but at the end of the day, we need to convert those probabilities into discrete pixel values that a computer can actually display.
Right, because an image is just a bunch of pixels. So the decoder, is it like a translator?
You could say that. It takes those continuous probabilities and assigns a probability to each possible pixel value.
So it's like the model is painting with probabilities, and then the decoder comes in and chooses the most likely color for each pixel.
Exactly. It's the final step in turning those abstract probabilities into a real, tangible image.
This is all really complex, but it's super interesting to see how it all comes together.
Yeah, it really is a testament to the power of deep learning.
Well, that was a lot to take in, but I think we've got a good grasp on the core technicalities of diffusion models now.
I think so too.
Okay, so we've gone over like the basic building blocks of diffusion models. We talked about the forward and reverse processes, the variant schedule, unit architectures, the training objective, and even the decoder that brings everything back to the pixel level.
Yeah, we've covered a lot of ground.
But I'm really curious to dig into some of the like more advanced concepts that our sources mentioned.
Sure, happy to dive deeper.
So let's start with checkpoints. I've seen this term pop up a few times, but I'm not really sure what it means in this context.
Well, a checkpoint is basically a snapshot of a trained model. It's like saving all the model's parameters and configurations at a specific point in time.
So it's kind of like saving your progress in a video game so you don't have to start over from the beginning every time.
Yeah, that's a good analogy. And it's really useful for a bunch of reasons. For one thing, it makes it much easier to share trained models with other people.
Right, because you wouldn't want to have to share all the training data and everything every time you wanted to collaborate with someone.
Exactly. And it also saves a ton of time and computing power. Instead of having to retrain the model from scratch, you can just load the checkpoint and pick up where you left off.
Makes sense. So checkpoints are basically a way to make the whole process more efficient and collaborative.
Exactly.
Okay, cool. So what about hypernetworks? I think I saw that term in one of the blog posts. What are those all about?
Oh, hypernetworks are really interesting. They basically allow you to, like, customize the style of the generated images.
Wait, so you can actually control the style of the output?
Yeah. So instead of having one model that always produces the same kind of images, you can have a separate, smaller network called a hypernetwork that modifies the parameters of the main model.
So it's like having a style guide for your AI artist.
That's a great way to put it. The hypernetwork learns to adjust the main model so it generates images with certain stylistic features.
So if I wanted to generate images in the style of, like, Picasso, I could train a hypernetwork on a bunch of Picasso paintings and then use that to influence the output of my diffusion model.
Exactly. The hypernetwork would learn to capture the essence of Picasso's style, and then it would guide the main model to produce images that look like they were painted by Picasso.
Wow, it's amazing. It opens up so many possibilities.
Yeah, it really does. And the cool thing is that training a hypernetwork is relatively fast and efficient because it's much smaller than the main model, so you can experiment with different styles pretty easily.
Okay, so we've got checkpoints for saving and sharing models, and hypernetworks for controlling the style of the output. What else?
Well, there's one more technique I wanted to mention called textual inversion, and this one is really powerful.
Textual inversion, what's that all about?
So it basically allows you to teach the model to understand new concepts, even if those concepts weren't in the original training data.
That sounds almost magical. How does that even work?
It's a bit technical, but I'll try to explain it simply. In a typical text-to-image model, you have a text encoder that converts words into a numerical representation that the model can understand. But this encoder is only trained on a limited set of words and phrases.
Right, so if you try to use a word that the encoder hasn't seen before, it won't know what to do with it.
Exactly. But with textual inversion, you can actually teach the encoder to understand new words by associating them with specific images.
Oh, I see. So if I wanted to generate an image of, like, a purple flying elephant, I could show the model a few pictures of purple flying elephants, and it would learn to associate that phrase with those visual features.
Yeah, that's the idea. You basically create a new token for that phrase, and then you train the model to link that token to the visual representation of the concept.
That's incredible. So you can actually expand the model's vocabulary, so to speak, without having to retrain the entire thing.
Yeah, it's pretty amazing. And it only takes a small number of images to do it, too. Like 3 or 4 images is often enough.
Wow, that's some seriously powerful stuff. So we've got checkpoints, hypernetworks, textual inversion. It seems like there's a whole toolkit for customizing and controlling these diffusion models.
Yeah, there's a lot of potential there. And this is still a relatively new field, so I think we're only just scratching the surface of what's possible.
Okay, so we've talked about like all the technical details of how these diffusion models work.
Yeah, we really got into the nuts and bolts.
But I think it's important to step back and, think about the bigger picture for a second. Like, how are these models actually being used in the real world?
That's a great point. I mean, it's all very cool in theory, but what kind of impact are they having out there?
Exactly. And our sources actually touch on some really interesting applications, so I'm kind of excited to dive into that a bit.
Me too.
So one area where these models are making a big splash is art and design.
Oh yeah, for sure. Artists and designers are using them like as creative tools to come up with, unique and imaginative visuals.
I've seen some of the stuff that people are creating with these models, and it's seriously impressive.
Yeah, it's pretty mind-blowing. I mean, they can generate anything from like photorealistic landscapes to these totally abstract and surreal compositions.
Right. And it's not just about the quality of the images. It's also about, like, making art creation more accessible.
Totally. Anyone who can, learn a little bit about how to use these models can start creating art, even if they don't have any traditional artistic skills.
So it's like democratizing art in a way.
Yeah, exactly. And it's not just limited to still images either. People are using diffusion models to create animations and even 3D models.
Wow, that's cool. I'm really interested in, like, the potential for these models in entertainment. Like, imagine generating characters and environments for movies and video games.
Oh, yeah. Or even like virtual reality experiences. The possibilities are pretty endless.
It could totally change the way we think about, storytelling and world building.
For sure.
But it's not all fun and games, right? I mean, there's some serious applications for this technology, too.
Absolutely. I mean, one really promising area is medical research.
Oh, right. Our sources mentioned that.
Yeah.
How are they being used in that field?
So they can be used to generate synthetic medical images, like, images of different organs or tissues.
And why is that useful?
Well, for one thing, it can help researchers train diagnostic algorithms, the algorithms that are used to detect diseases and stuff.
Ah, so instead of having to rely on, like, real patient data, which can be hard to come by, they can use these synthetic images to train their algorithms.
Yeah, exactly. And it can also help with visualizing complex medical data, making it easier for doctors and researchers to understand what's going on.
I see. So it's not just about creating pretty pictures. It's about using these models to, like, solve real-world problems.
That's right. And I think we're just at the beginning of exploring all the potential applications of this technology.
Yeah, it really feels like we're just scratching the surface.
Definitely. It's an exciting time to be involved in this field.
So to wrap things up, we've gone pretty deep into the world of diffusion models. We've talked about how they work, the technical details, and some of the amazing applications. It's clear that this technology is already having a big impact, and it's only going to get bigger in the future.
Yeah, I think that's a safe bet.
And for our listeners, I hope this deep dive is giving you a better understanding of this, like, super cool and powerful technology. Thanks for tuning in.
Always a pleasure.